Hi, we're doing homework 2A for statistics, Map 146 today. Starting off talking about summarizing and graph data. So we'll take a look at what the screen says, and then I print it off so I can work it over here on the thing. So when you're asked the question, what's the class width? Here, notice we have 1, 2, 3, 4, 5, 6, 7 classes. The classes are those, each little category that we have. So we have 7, which is, so we have midpoints for each of those. We have 7 midpoints that we're going to find. And we also are asked, what is the class width? And the class width you take by taking your lower class boundaries. So in this first class where you have 40 and 44, the lower class boundary is 40 and the upper class boundary is 44. So those are two terms that you should know from the notes or whatever. And you just subtract two, what do you want to call it, adjacent lower class values or upper, whichever. So you have 45 minus 40 is 5, so that would be our class width would be 5. And then the midpoint, a midpoint is an average of these two. So you would add 40 plus 44 and then divide by 2, and that would tell you the midpoint of your class. And so we're going to do it on this other one, which has different numbers on it, but that's what that looks like. So let's jump over and take a look at the paper version. First of all, you should be able to look at those now and tell me what the class width would be. Again, we have 7 classes. They're different than the last ones. So you're going to subtract 2 adjacent lower class boundaries. And when you do that, 35 minus 32, you get a class width of 3. All right, and then, does that seem a little fuzzy? I can't tell. Where's the auto focus? I'm afraid to do anything, but sometimes if you zoom, then it'll focus a little better. And that's what we get. Okay, so the midpoint, we're going to do it for each, we could do it for each one if we wanted. 32 plus 34 for the first one, and then divide by 2. And that's going to be 66 divided by 2, which is 33. So our first midpoint is 33, and then we could go through and do that for each one of these. But if you take 35 plus 37 and then divide by 2, you get 36. So the next one would be 36. But also, once you know what your class width is, your midpoints are that far apart as well. So if the first one's 33 and we know the next one's going to be 3 more, then we get 36, and 3 more is 39, and 3 more is 42, and 3 more is 45, and 3 more is 48. And you can see that those are working perfectly. They're right in between there, and the last one's 51. So all you really have to do is calculate the first one and then start adding your class width, whatever it is, and you'll get all the rest of those. Now the class boundaries are this. So let's say that I had, these are my boundaries, and I had, some books will do it differently, but this book says, let's find a midpoint. So we always go a little more specific than our actual classes were. So the class boundaries here, we're going to take off 0.5 in either direction. So we're going to say that we start with 32 minus 0.5, and that gives us 31.5. So we're going to have 31.5. I can't really fit in those boxes very well. 31.5 over here, and then if you jump to the other side, you're going to add a 0.5 over there, so we have 34.5. And they don't want you to write it twice. Just checking. So that would be 34.5, but so would this one be 34.5 because that's half of that, so you don't have to write that again. Half more than 37 would be 37.5. and half less than 38 is also 37.5, so you don't need to write it again. 40 and a half, 43 and a half. You can see what's happening here is these boundaries are also going up by 3. 31.5, 34.5, 37.5, and once you realize that, you can just be going, okay, and then 46.5, 49.5, and 52.5. So you're always going up half of greater, but because of the class width being 3, they're always like that. And that is that one. Okay, so again, I'm going to work them on paper, but I'm going to jump back and forth just to make sure that you see how to enter them, but really that should be pretty straightforward. You enter your midpoints there and then your next one. They hate it when you leave a question, but I'm really going to leave it. That's why it's counting it wrong. So for this one, it's the same type of thing. And what I'm going to typically do on all your homework is show you one example and then let you figure those out for yourself. I'll show you what's different about this one, but for the class width, that's not different. You're just going to subtract to get that. For the midpoints, not different. You're going to add the two together and then divide by 2. And then you're going to add that class width on every time. But what's a little different, a little harder about this is the class boundary. So let's take a look at that. Let's look at my paper. So we have this a little more complicated because it's out to the tenths place. So when I look at class boundaries before, what I did was just added 0.5, took 0.5 off, or added 0.5 to each one. But 0.5, we're already that specific, so you need to go out one more and go out to 0.05. So you're going to subtract 0.05 from both of those. And where do they start that? So you start with 57 and subtract 0.05. So you're always going out one more place. The specificity on this was to the tenths, so you're going to go out to the hundreds. If it was already to the hundreds, you'd go out to the thousands. You're always going one more than we did before. So here, when we had whole numbers, we subtracted 0.5. And now that we have tenths, we're going to subtract 0.05. And maybe you see that pattern as you're always doing that. And so 57 minus 0.05 is 56.95. And that would be my first one. And then in this one, my class width was 57 minus 60 minus 57, or 3 again. So then I know my next boundary would be 3 more than that, which would be 59.95, and then 3 more than that, and 3 more than that. So it's very nice because all I have to do is find the first one, and then I know I can just be adding that class width on the rest of the way down. But just take note that if it's to the tenths place, we have to go out to the hundreds in order to get those class boundaries. Okay, let's see what we have next. So in number 3, they're talking about, they have this data set, by the way, which you click on to see all of it. So you can't see it unless you click on it. And they do show me that, okay. So they have these, and then they ask you to give the relative frequency for the non-filtered and the relative frequency for the filtered. And you can see that there's 2 different sets of data there. And I think those are different, yeah, than mine. So let's go over and see what I have. A relative frequency is just a way of, it's like a frequency, but you divide by the total number possible. So that's all there is to it. So we have to see, here's my relative frequency down there at the bottom. So for non-filtered, do you see that in non-filtered, the amount of tar that's between 4 and 9 is 0? There's no tar in that, so it's just 0%. Also, between 10 and 15, there's nothing, so that's also 0. So the first one we can actually get an answer for is the 16 to 21 category. So what we're going to do is add all these up. That's 21, 22, 23, 24, 25. And for 16 to 21, there's 1 out of 25. So we're just going to take 1 and divide by 25. That's the relative frequency. 1 out of 25 is 0.04. Which, if I move that into actual percent form, is 4%. Right? It's 0.04 which is 4%. I didn't write that dark enough for you to see it, but anyways. So the next one, 22 to 27, well, it's twice as much as the last one, so it should be 8%, but we can just check it. So it's 2 out of 25, 8%. 14 out of 25 for the next category. It's 56%. I am getting a decimal and moving it over 2 places to get the percent. 34 out of 17 is half of that, so it should be 28, but we take 7 divided by 25 and we get 28%. And then the last one is 1, which we did earlier and found that to be 4%. If I've done this correctly, what will all these percentages add up to? They add up to 100. These are the non-filtered. So notice if you don't filter your cigarettes, there's no cigarettes that have this low amount of tar. And then we have a lot of tar here, but we don't even with non-filtered, don't get more than about 40 grams of tar, it looks like, milligrams of tar, sorry. Okay, so for the other one, we have a different thing. Here they're filtered. And notice that we have down here in these lower ranges, but we don't have any in the higher ranges. We don't have any in the 40 to 45 or 34 to 39. But we do have one. We can add these up again, 21, 24, 25. There's 25 total. And so for the filtered 1 out of 25, we already know 1 out of 25 is 4%. 3 out of 25 is 3 times 4, 12%, but you can just check that. Just if you don't feel comfortable, go ahead and, whoops, not 12. It's 12 because 3 divided by 25, it gives us 12. And then 5 would be 20%. And then 16 is 64%. So most of the cigarettes that fall into that, the filtered category fall into there. And then we don't have any at 28 to 33, at 34 to 39, at 40 to 45. So if your cigarette is not filtered, there's a chance, a very small chance, that you could get lower amounts of tar than these people that have filtered cigarettes. But in general, we could say here's where the zeros are up here. For the non-filtered, don't have low amounts of tar. For the filtered, don't have high amounts of tar. So the question is, do you think that these filtered cigarettes appear to be effective? And I would say yes, because the relative frequency of the higher tar classes is greater for the non-filtered. This is greater over here. So I would say yes, it is rather effective. Okay, so it's just dividing by that number. All right. Done with that. And here we want to look at the set of data again. You have to click on that to see it, and then build a frequency distribution with 5 classes. Begin with the lower class limit of 120.9 and use a class width of 0.2 volts. Does the result appear to have a normal distribution? Why or why not? So the class width is 0.2. So that means this. I'm going to take you over here to my thing in a second here. Get rid of that. That's the same thing I got, so that's good. All right. You don't want to see what I'm seeing. It's all messed up, but I'm about to get it right. Okay. So it's the same thing. If you click on the icon, you get this data that's down here. So that's what I'm looking at. But it told us to make classes with a lower class of 125.6. That's because if you look at our data, that's the smallest data value that we have. So we're going to go here because it says it's going to be 0.2. And remember, the class width is about these two guys. So right here, I'm going to say 125.8, okay? And then the rest of them are going to be similarly spaced. So 125.8 and then plus 0.2 is 126.0. And then 126.2 and then 126.0. 0.4. I'm adding 0.2 on every time. What goes over here though? Well, that's where you want to be careful. The class width doesn't tell you the width between its own class boundaries, but between two boundaries. So we want to take 1/10 off. Since we're going tenths by tenths here, you want to take 1/10 off. So that's 125.7. And then you can just go up by 0.2 here, because always the class width helps us do that kind of thing. Then 0.9, 126.1. It's also 1/10 less than that, but we can just do it down the row here. 126.3 and 126.5. So that's how that's going to go. And then we have to do the frequency. So to do the frequency, we're going to go through here and check off each one where it goes. So 125.8 is here in this one. So this is this 126.2 is down here. 126.0 is here. 126.3 is here. 126.2 is also there. 125.6, and this is kind of a yawn and a half, but we have to do it. 125.6 is up here. 126.1. The data is just sort of like, who cares about this data? And it's really not hard to find interesting data, so I apologize that we used boring stuff here. 126.2, 126.1, 125.7. That's up here. 126.1, 126.0, 126.2. 126.1, it's just tedious. You just have to get through it. 125.9, 125.8. Maybe you'll see me make a mistake and you'll cringe, but I'm not going to go back and redo this. If I put something in the wrong category, then that's bad on me. But at least you'll be able to check it by the computer. Since I'm doing it on paper, I won't get that feedback. But I think even if I make a mistake, it won't lead you that far astray, because you see what's happening here. You're just putting these into their categories, and 126.0 is here. So the frequencies that I have is 2, 6, 10, 6, 1. And that's 10, 22, 23, 24, 25, and that's how many things I had, so that's good. And the question is, does this appear to have a normal distribution? A normal distribution by nature starts low, goes up to some peak, and comes back down again. So if you look at our data, it kind of has that shape, right? It goes up, comes back down. That's a bad drawing, but it does have a pretty normal distribution. Even though it's 2 on one side and 1 on the other, it's roughly normal. So yes, the frequencies start low, reach a maximum, and come low again, so they're relatively symmetrical. So it is pretty much a normal distribution. All right, let's go back here. Just do it. Okay, use the given qualitative data to construct the relative frequency distribution. 2,467 people aboard a ship that sank include 510 male survivors, 1,542 males who died, 333 female survivors, and 82 females who died. Complete the relative frequency below. So I'm not going to go through a ton of this, but we'll go through a little bit of it, just to make sure, because one of the things they say about people that don't do well in statistics is they're bad with decimals, fractions, and percents, because that comes up a lot. So I just want to make sure that you know how to do that, and if you're weak on that, you should email me and get like a video you can watch on percents or something so you can get up. Anyway, the pilot, this one's a little different. Among fatal airplane crashes that occurred during the past 65 years, 482 were due to pilot error, 93 human error, 203, oh, that's a different problem. That's why it looks so different. Yeah. Okay, let's actually do number 5. There were 2,341 people on board. So to decide the percent that were male survivors, you just take the male number that you were given there 379 for male survivors, and you divide by the total number of people that were on board. And then you get, you don't want to do this without a calculator, get a calculator. Round to 1 decimal place as needed. So we have 0.162, and when I move that over, I get 16.2%. When they tell you to round to 1 decimal place, that's your final answer should have 1 decimal place in it. You don't want to round here and get 0.2 because that's not what they want. They want your final answer to be rounded. So this would be 16.2, and you do the same thing for each of these other categories. And when you're finished, your percentages should add up to 100. Okay, so this one is very similar, so we'll just go ahead and look at number 6 without going back to the other screen. So there were 482 pilot error accidents, 93 human error, 203 weather related, 228 mechanical, and 188 were due to sabotage. Construct the relative frequency distribution. What is the most serious threat to aviation safety, and can anything be done about it? So what you're going to do first is add up to find out what's the total number. We had 482. 65 years is not something we're adding in. 93, 203, 228, and 180. So we're just going to add this up to find out what our total sample space is here. 482 plus 93 plus 203 plus 228 plus 180 is 1,186. That was poorly written, sorry. And then we're going to go through and find each one of these. Pilot error was 482 out of 1186. And then we're going to get that answer. And they want us to round to 1 decimal place, so we're going to go out to 0.406, and we move that over, we get 40.6%. That's pilot error. And you're going to do that for all 5 categories. And then the last question says, what's the most serious threat to aviation, and can anything be done about it? The most serious threat is going to be the highest percent that you have, whatever that is, and then you can say whatever it is. They have a little, if it's pilots, they could be trained better. If it's mechanical problems, they could be maintained better, that kind of thing. So that's how you're going to do that question. Okay. So that one looks just the same. Yep. And then number 7. What characteristics of data is a measure of the amount that the data values vary? So we have what we call measures of central tendency, and different that kind of are looking at different things. But when we talk about how much does the data vary, like if we're interested in how far do people drive to get to South Puget Sound Community College, and we're wondering, like, do some people drive further to go up to Pierce because they don't like South Puget Sound, or do they drive further and not go to Centralia because they do like it? Maybe we're trying to find out, like, how big of a draw do we have. And so when we get the data, we want to know the average because that's a nice measure of center. But we also want to know, like, what's the variance? I mean, there are people that live up on Tumwater Hill that are walking down half a mile, and there's people that live down in, or up in Shelton or down in Centralia or whatever that are driving quite a ways. That spread, that's the variation. So when we talk about the variation of the data, that talks about the way that the measure is spread out. That's the variation, and that's another measure for that is the standard deviation, and the variation look at what's the spread of the data, because you could have data that if you looked at it doesn't have to be it could be like this, where the data is mostly centered right in there, or you could have a lot of spread and the data looks like this, where it's all spread out and not grouped together like that. So the variation is what we look at for that. Oh, I didn't show you what I was talking about. I looked at you, but I didn't show you the picture, so we'll just jump to that really quick. What I was saying about the variation is that the variation, if it doesn't have a lot of variation, it could be very peaked. And if it has a lot of variation or a lot of spread, you're going to see something like that. So it's the variation that we're looking at when we're talking about the spread of the data. Okay, so this one, number 8, what are sample values that lie very far away from the majority of the other samples? And obviously, if it lies very far away, calling it the center would be ridiculous. So that's not a good one. But it's the outliers. We call outliers those one that are really far out. So let's say that because somebody has a spouse that works in Olympia, they decide I might as well ride with them every day and hang out with them in the car. So I'm going to go to school at South Puget Sound Community College even though I live in Vancouver or whatever. So you're driving that far. That would be an outlier, kind of a weird, unexpected case. Sometimes we throw those outliers out because they really distort the values a lot. But that is an outlier. Okay. A blank helps us understand the nature of a distribution of a data set. Well, when we're doing these things that we did in the first couple of problems, where we have the classes and we have the frequency, those are frequency distributions. That's what that is. They're when we have the charts and we have everything broken up. That's a frequency distribution. So it helps us understand the nature of the distribution of a data set because we can look at that and say, well, does it look like, when we answered the question a little bit ago about does it look like a normal distribution, by looking at this frequency distribution, we saw that, yeah, it kind of gets small, gets big, goes back down. So frequency distributions help us answer questions about the look of the data, that kind of thing. So that would be a frequency distribution. All right, I know I'm not switching back to there. I will if I think that it's important. Okay. All right, in a blah blah distribution, the frequency of a class is reported as a proportion or percent. Well, we already did a couple of those, so it shouldn't be that much of a surprise. That is here. When we gave things as a percent, that's called the relative frequency, right? So a distribution is just not percentages, but just the number. That's just a frequency. That's just a frequency distribution. Once we change those into percentages, then that's a relative frequency. That's the difference between those two. So we have a relative frequency when we talk about a proportion or a percent. As a percent, we actually put the symbol. As a proportion, it's left as a decimal. So those two things are a little different. Okay. All right, so now we have this one. Let's jump and look at number 11 on the computer just to kind of see that. The histogram to the right represents the weight in pounds of members of a certain high school debate team. What is the class width and what are the appropriate lower and upper class limits of the first class? So the class width, approximate, sorry, not appropriate, approximate. The class width is how far apart it is. This is like a lower class boundary right here, 105. And this is another lower class boundary, 125. So in order to find those, we would just subtract. That's what we've been doing. That's what we're going to do again. So go ahead and look at my number 11. And I start with 100 and it goes up to 120. So if I subtract those two, then I get a class width of 20. All right. Approximate lower and upper limits, well, that's it. I mean, you have a lower limit of 100 here. This is of the first class. If we were asking about the second class, it'd be lower of 220, upper of 240, right? But the upper class limit is about 120. Now, if I was going to write that, I might end up doing 100 to 119, and then the next one starts at 120 and goes whatever. So 20 up, so it'd be 139, right? So I could write that, but it's approximately, as we look at it, about 120. So I think that's kind of what they wanted, yeah. Okay, so that's what we're asking. All right. A frequency distribution below represents frequencies of actual low temperatures recorded during the course of a 31-day month. Use the frequency distribution to construct a histogram. Do the data appear to have a distribution that is approximately normal? So look at your data. It starts low at 1, it grows to 11, it goes back down to 2. So this makes no sense. And anyway, a histogram, we don't have spaces in between. These are bar graphs. A and B are bar graphs, but they are not histograms. Histograms are, because they're talking about data, we don't want to have a gap there, so we want them all to press up next to each other. So it has to be C or D, and I will let you figure that out. That cannot be complicated for you at this point. All right, so this is another one where we're going to pick the graph and choose the correct histogram based on the data. So your first one's going to be 3, your second one's 3, then it goes up to 8. Here it looks like this one starts at 7 or something, so that can't be it. This one looks pretty low, and then they jump up right away. So the only one that really makes sense for us that I see is this one, C. And it says, does the histogram appear to depict a normal distribution? You know, it doesn't have to be exact to be normal. And then why or why not? Well, it appears to me to be rather normal. It starts low, it gets high, and it goes back low again. The frequencies generally increase to a maximum and then decrease. It's roughly symmetric. So I would say this one. It's not perfect, but it's roughly. All right, so that's something to think about. And this is the same question, so I'll let you answer that one on your own. They give you the numbers here. You want to come over and say, okay, the first one's 20, second one's 12, the third one's 5. That doesn't make any sense here. You pick which one, and then you say whether you think that that graph looks normal or not. So I think you can do that. This was the same type of question. We want to, given the data, we want to pick the histogram that goes with it, and then we want to say, is it normal or not? And why or why not? Does it build and go back down, or does it not? So you're going to do that same process. The heights of the bars of a histogram correspond to what values? Well, let's just go back to number 15. What do they always have here? Or 14? Or 13, 12. The numbers over here are going along with what we see here. The numbers on the bottom go with the classes, and the number along the side always go with the frequency. So the heights of the values, or the frequency, are the number of times that occurs, whereas the horizontal axis is the classes themselves. And the bars in a histogram, they do touch. Is that what they want? They are labeled. That's not true. They don't have equal heights. That's not true. And they have unequal widths. No, it's just that they touch. They always touch in a histogram. Otherwise, it's just a bar graph, and that's not what we want. Is that the end? Wow, that was quick. All right, have a great day. I'm going to do 2B coming up next, and I hope you have a fantastic rest of your day.